Okay, our next section is 5.8, and as you know, we were dealing with inequalities in graphing yesterday, so we can just step it up one, and we're going to graph several inequalities, or what we have been calling a system of linear inequalities in section 5.8. So you can see we're going to recognize properties of those systems, and we are going to solve those systems by graphing. So let's get to that. A couple reminders as we graph. When we say we're going to graph a system, you got to think about all the characteristics you use for inequalities because they will all be used. And then now a system means we're going to have two or more, okay, on the same one. So it could get pretty crazy if you got all that shading. So we're going to come up with a couple things here that you could do to help solve that. So step one, graph the first inequality and shade. So our first inequality was here in yellow. Y is greater than 2x minus 5, so double check my graphing. It already is in slope-intercept form, so we can see that the y-intercept was a negative 5 and the slope was 2. So let's check that. We went down to a y value of negative 5. 1, 2, 3, 4, 5, there's the point. And from there, I graphed a slope of 2, up 2 over 1, up 2 over 1. You can see that. I drew my line. Now, the one thing that's not showing up real well here is that I drew my line dashed. So we're going to redraw that with our tool and make sure that it is dashed so you can see it accurately. So y is greater than, drawing it. I'm putting it right over another one. That's why it's not liking it right now. I will move it a little up, a little too far. Okay, so we can see our line should be dotted because of the greater than sign that we have. I'm just trying to get it lined up with the rest of other points. Good enough for now. You got the idea. Okay, so we would have graph the inequality, use x and y intercepts, and we would have shading because y is greater than, and that's this side of the line. So when we graphed that side of the line, we used our yellow and had our arrows going in that direction thinking-wise. Okay, then we were supposed to graph, I believe, the second inequality on top of that. So you're going to see the second inequality come in now. And if you remember the equation, let's just do a little work here. 3x plus 4y is less than 12. Let's write that on our new graph. 3x plus 4y is less than 12. If we did c over b and c over a, got our y and x intercepts in, 12 over 4 would be our y-intercept, and c over a would be 12 over 3, which is equal to 4, which is our x-intercept. Okay, so from there we got a y-intercept of 3 and x-intercept of 4. We're going to graph those 2 points. Y-intercept of 3 and an x-intercept of 4, so y3, x is 4, there they are. And we then draw our line. Again, it's a less than in our original, so we should be able to see that that we have 2 inequalities now on this, and they are both dotted or dashed lines. And from there we shade, and we're shading only the blue line, which is y is less than, which is in this direction. If you remember, we had the yellow shaded in this direction. And so now when you look at what's left, there is a double shaded area, and we're going to pull that up on the next graph, and it turned green. Obviously, yellow and blue make green in this case. And when that happens, we get this shaded area that is the solution of the system. That double shaded area is what we need. So, not to make your graph so crazy, you could use colors, like we just did, or you could use the combination like I did to start, and that was, let's take our pen tool, and just draw, where do I need to shade? And on for the yellow line, I need to shade here. And I would have done this. Just real easy and light. It could be erased later. And then for the blue line, I'd be shading here. And then you can see where you need to shade for the double shading. And so you would shade only that region on your paper, and you wouldn't have the colors and stuff overlapping. Identify the solution. All points in that region are parts of our solution. So here it says, shade the graph. So we're going to try it. We've got the two lines already drawn. You can sort of see the x and y axis again. Let me identify the origin so we can keep track of it. There's 0, 0. What part of the graph represents the solution of this system? Well, of course, their intersection does. But let's start with y is greater than x minus 2. So you said, all right, that's a y-intercept of negative 2. That's right here. And from there, up 1 over 1, up 1 over 1. And from there, we get up 1 over 1 several times. Get our line in black. From there, go to the red one. It's a y-intercept of 3 and a slope of negative 1/3. You can go ahead and graph that. You would see the line in red. When you shade, we now need to be shading two different directions. Let's use our little arrow idea. Y has to be greater than our line in black. So greater than would be here in this area. And make sure you do it well down the line because you don't know what's going to happen. And then our yellow one, y is less than or equal to. So less than that line would be here. And again, you can see where is that part that should be double shaded. And we have it there. And let's move this down. And we need to be in this region right here. So what part of the graph represents the solution of the system? Any point inside of this region and on this line in red, but not the line in black, would be a solution to this system. If we have to find vertex points, now let's say that your region that has been shaded is now a closed region, not infinite like we were drawing on our last graphs. You should be able to identify these vertex points. When I say vertex points, these corner points. So I should be able to identify that, that, and that. This is going to be key as we move forward in our work. So this feasible region, where could your solution be? If we find the vertex points, we have to find them exactly. We can't guess. Now on this one, it's not going to be too bad because everything's vertical and horizontal. We do have the one diagonal line, but I think we can get what we need. So if we look at this, we can just count and say, okay, that was 1, 2, 3, 4, up 2. It lands on it, so we're looking at negative 4, 2 for that one. Over here, we're on an x-intercept, which we would have had labeled as part of one of our C over B, C over A work in one of the equations. And this last one happens to be the intersection, also a y-intercept of both of these lines, so we should be able to say 0, 2. Finding these vertex points is going to be key. Now, what I want you to think about, though, is what if I would have had a region that was more like this? And my points don't land exactly on whole number values. You still should be able to find those vertex points. So in this case, right there, right here, and here for the third one. We have done this already in our work. How do you find that point of intersection? Well, solve a system. We have graphing, and if that's not good enough, we used linear combination. If we didn't think that was good enough, substitution was an option, and so were matrices. So we have all of these choices. You just need to take and identify your lines carefully enough, line A, line B, and line C, in your work so that you can identify which two equations you need to use to get your point of intersection. And then I personally would use either substitution or linear combination. In this case, our first case, we didn't have to because everything was nice. However, real world, everything is not so nice. This feasible region is an example of one that I was just discussing. What if everything is not exactly like we want it? They appear to be just off. Okay? So an example here, and I have everything color-coded to show you, we would need those three points of intersection. But those 3 points of intersection come from where the lines intersect. So if we start looking, if I want to define where this red and black line intersect, which is this point right here, I'd be taking the equations y equals 2x plus 2, which represents the red line, and y equals 1x plus 5, which represents the black line, and I would be able to solve those. Now, right now, I could get rid of the y's in both of those equations. So if I have them stacked like that, and I now subtracted those two equations, get rid of the y's, y minus y is 0, 2x minus 1x is x, and 2 minus 5 is negative 3. So if I move the 3 over, my x value comes out to be 3. And something's not quite right there. Because I'm looking at this, 1, 2, 3, 4, 5, 1, 2, up 2 over, oh, that red line, up 2 over, but that's how you would start working, and then I do the y value, but I can see that we got a slight problem, because this red line has a y-intercept of 2, but then the slope is up 2 over 4, which is 1/2. So now let's do the math if that was a 1/2, and let's see what we get. Let's see if the black line's right too before I start. 1, 2, 3, 4, 5, and then down 1 over 1. Yeah, black line looks okay. So now I subtract 1/2 take away 1x should leave me with a negative 1/2 x. 2 take away 5 is negative 3. If we add the 3 to the other side, we get 3, and we still have our negative 1/2 x. So now we're going to have to multiply by negative 2 to undo that. And we get x equals negative 6, which is closer to what we need. 1, 2, 3, 4, 5, 6. Yep, definitely. Okay, so x is negative 6. If x is negative 6, let's put it back into either one of those equations. I'm going to put it into the red one. Y equals 1/2 times negative 6 plus 2. That'd be negative 3 plus 2, which is negative 1. Y equals negative 1. So we would get the ordered pair negative 6, negative 1 for our exact solution. 1, 2, 3, 4, 5, 6, negative 1. So they're saying it's really crossing right here, even though our graph didn't look like it. So there would be the first vertex. And then we would go into the red and the blue line for this point. And then we would do the black and the blue for that point. And we would end up with exact vertex points for our problem. Not just guessing at what they are, because we need exact for our next step in our chapter, in sections 5, 9, and 510. So in order to do this, feasible region, systems, I think we're good. We just need a little practice and some time doing the problems.